Inductor. Inductor is a basic passive circuit component and it is used in an electronic circuit. It is a coil of conducting wire wound on a suitable core. The core may be iron, air, ferrite, etc. Here figure shows the conducting wire wound on the core having length L and current is flowing through the wire is I. Here number of turns N wound on the core and cross-sectional area A, and voltage is developed across the wire is shown in V. Here symbol of the inductor is shown. Is the property of an inductor to oppose the change of current flows through it, and it gives the formula V is equal to L into di by dt, and L is equal to N square mu into A divided by L, where N is number of turns of the wire, then it is a constant, A is cross sectional area, and L is the length. Inductor is measured in henries. Also there are other units like millihenry and microhenry. The inductive capacitance is induced in the coil and it is given by the letter XL, and XL is equal to 2 pi F. After that we seen types of inductor. Depending on the type of core, there are three types of inductors. First is air core inductor, where air acts as a core. Then iron core inductor, in this iron acts as a core, and ferrite core inductor, where ferrite acts as a core. Firstly we seen air core inductor. This is the symbol of air core inductor, and this inductor is made up of coils of wire and these are wound on the former. In this inductor, core is completely absent, air itself acts as a core. These inductors offer high reluctance path for the magnetic flux, hence less inductance is here. The air core inductors have larger coils to produce higher flux densities, and these inductors are used in high frequency applications like TV and radio receivers. After that we seen iron core inductor. This is the symbol of iron core inductor and it looks like that. This inductor is made up of coils of wire wound on a solid iron core, and due to their higher magnetic permeability, these have high reductance property. These are high power inductors but limited in higher frequency capacity due to the hysteresis and eddy current losses. Iron core inductors are suitable for audio frequency applications. Then ferrite core inductor. This is the symbol of ferrite core inductor and this looks like it. Ferrite core inductors are made up of coils of wire wound on a ferrite core. Ferrite oxide. Ferrite is a metal oxide ceramic based having mixture of ferric oxide, that is Fe2O3. These having advantages of decreased cost and low core losses at high frequencies. Soft ferrites are used for core construction to reduce the hysteresis losses, and these are used in high frequencies applications. After that we seen self-inductance. Self-inductance is a phenomenon of inducing EMF in the self coil due to change in current and hence the change in magnetic flux in the coil. The induced EMF opposes the growth of or decay of current in the coil and hence delays the current to acquire the maximum value. Self-inductance is also called inertia of electricity as it opposes the growth of decay of current. Self-inductance is given by the equation phi is directly proportional to I, or phi is equal to L into I, where L is the constant of proportionality and known as self-inductance or coefficient of self-inductance. If I is equal to 1, then L is equal to 5. Thus, self-inductance is defined as the magnetic flux linked with a coil when unit current flows through it. Also, E is equal to minus d phi by dt, or E is equal to minus L into di by dt. If di by dt is equal to 1, then L becomes is equal to E. Thus, self-inductance is defined as the induced EMF set up in the coil through which the rate of change of current is unity. Then mutual inductance. Mutual inductance is defined as the current flowing in the one coil that induces a voltage in an adjacent coil. Here figure shows the mutual inductance where there are two coils, coil L1 and here coil L2, placed near one another. At that time the mutual inductance is produced in this because of first coil there is a voltage is developed across the another coil L2. These are the mutually coupled coils and these are the lines of magnetic flux which are produced between these two coils. If the distance is large, then these lines of magnetic flux are becomes wide. And the formula for mutual inductance is given by mu naught into mu r n1 n2 into A divided by L, where mu naught is the permeability of free space, then mu r is the relative permeability of the soft iron core, n is the number of turns of coils, and A is the cross-sectional area in meter square, and L is the length of the coil in meter. Then Lenz's law. It states that the direction of an induced EMF is such that it will always opposes the change that it causes it. Here in the figure there are four types of direction of the induced EMF is shown. Here is the first figure, then second is here, then third is here, and fourth is here. Then Faraday's laws. It states that the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux through that loop changes with time, and it is given by the equation E is equal to minus d phi into B divided by dt. This is Faraday's law. If we change the magnetic flux through a coil of having n turns, and induced EMF appears in every turn, and the total EMF induced in the coil is the sum of these individual induced EMF, and it is given by the formula is equal to minus n d phi into B divided by dt, and where n is the number of turns of coils. Then inductor in series. The equivalent inductance of series connected inductors is the sum of individual inductors. The current I that flows through the first inductor L1 has no other way to go but pass through the second inductor and the third, and so on. The figure shows here inductor L1 having turns, then L2, L3 and Ln. These are the connected with series. At the inductor L1, V1 is voltage produced, L2 V2, L3 having V3, like that. And here is the equivalent of the series inductance, and it is given by the formula L equal to L1 plus L2 plus Ln, etc. Then inductor in parallel. The equivalent capacitance of parallel inductors is the reciprocal of the sum of the reciprocals of the individual inductance. Here In the figure, the inductors are connected with each other in parallel. Here is the L1 and current flows through the L1 is I1. Here is L2. Current flows through the L2 is I2. Here is L3 and current flows through this I3 and so on. Here is the equivalent of this inductance and it's given by the formula 1 divided by L is equal to 1 by L1 plus 1 by L2 plus 1 by Ln. Then applications of the inductors. Inductors have a wide variety and important applications in electronics. It is used in high power applications. Then it is used in transformers and by suppressing noise signal in the sensors, in the filters. It is also used in radio frequencies, used in energy storage, then isolation, motors